I'm Herb Gross, and welcome to lecture number 38 in our series Gateways to Algebra, where today we're going to, I guess we can say, introduce angular measure, measuring angles, even though indirectly we've already done this in the course. Let's see where we have done that, in fact. Remember when we talked about graphing straight lines and we talked about the slope? For example, what does it mean if I say to you that the slope of a line is equal to 2? It says, start at a particular point on the line, move 1 unit to the right, and for every unit you move to the right, the m equals 2 says what? You go up 2 units. In other words, go 1 to the right, and then go 2 units up. So 1 over, 2 up. I now draw the line that starts at the point P and goes through the point R, extends, of course, a line as such extends infinitely in both directions, and that slope, you see, indirectly has measured an angle for me. That line makes a certain angle with the horizontal, and I don't have to tell you what that angle is. By telling you that the slope is 2, you will get exactly that same direction. By the way, sometimes people say, well, how come you knew to go from P to Q? Why couldn't you have gone further? The important thing to remember is that the ratio, see, you're taking a quotient over here. You're going 1 over and 2 up. See, 2 divided by 1 is 2. But if I draw the same shaped triangle, see, if this was a photograph and I enlarged it, even though these sizes would be different, the ratio of this length to this length would be the same in the photo as it would be in the enlargement. In other words, to look at this from a different point of view, suppose this was the line, and somebody said, okay, let's take a look and see what the direction is. So I say, okay, let's go 1 unit over, and we'll go 2 units up. So then the line would be what? From here to here. But if instead somebody said, no, I want to go this far over and 2 units up, I don't know how well I've drawn this for you, but see, going 1 over and 2 up this way gives me a different finishing point than if I went this far over and twice as far up this way. But if I took this point, and this point, what would they do? They would fall on the same straight line. Now, people were measuring angles without using the word angle even before we talked about slopes. If you've ever seen a compass, not the compass you draw circles with, but the compass, you know, a magnetic compass or a compass that you use for direction, a directional compass, what we do is what? See, what we do is we draw a line that points north, and we label the arrowhead N. In the same direction, but with the opposite sense, meaning moving away from that, we label the other end of it south. Then, perpendicularly to this line, we draw a second line, and we label what? This point east and this point west. And now we can talk about what? North, east, south, and west. Now, of course, it's unlikely that a person will be going exactly in one of these directions. So, and look how vague it is to say, what direction shall I go in? So you say, well, go somewhere between north and east. That means I could go here. This would be doing it, wouldn't it? And if I went in this direction, that would be doing it. And if I went in this direction, that would be doing it. What am I supposed to do? You see, this is a geometric version of rounding off. With just these 2 directions, east and north, that's too much latitude, so to speak. So what we do is we draw some other lines. What we do is we split this angle in half. What we do is we now draw 2 more lines. And see what this line here is? This is halfway between north and east, so we call that northeast. This is halfway between north and west, so we call that northwest. This is halfway between south and east, so we call that southeast. This is halfway between south and west, so we call that southwest. And now if we say go between north and northeast, there's still an error, but now you're someplace where? In between these 2 lines rather than all the way into here. But by the way, you can just keep on doing this. In other words, why don't we split this angle in half? And if we do that, you start to see what's happening. See, halfway between north and northeast, we call that north-northeast. See, north by northeast. This one here is where? It's halfway between east and northeast, so we call it east-northeast. And you see what's happening? As I name more and more lines over here, the room for error when I say go between 2 of these lines gets smaller and smaller, but this also gets harder to memorize. Now, for example, during a war, you don't want people, say a guy's flying an airplane, or you're aboard ship, and there's a crucial situation. You know how people starting to think, is this east-northeast or is it east-east-northeast? They simplified it even more, but kept the same spirit. Basically, everybody knew how to tell time, so to speak. So what we did was we basically said, look, straight ahead will be noontime, so therefore directly behind you will be 6 o'clock. And then we talked about the hands of a clock. In other words, here's 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock, 5 o'clock, 6 o'clock, 7 o'clock, 8 o'clock, 9 o'clock, 10 o'clock, 11 o'clock. And so in a very easy colloquial way, you could give a direction here. See, in other words, you didn't have to measure what this angle was. All you would say to the person is, look at 1 o'clock. You didn't have to measure this angle. You would just say it's 4 o'clock. And this worked pretty good for quick approximations. It was the ancient Greeks, however, who gave us the type of angular measurement that most of us use today, and that was they took the circle and divided it up into 360 equal parts. In other words, each of those parts was called a degree, and they divided the circle into 360 degrees. Now you may wonder why they divided the circle into 360 degrees. It was done purely from the point of view of being able to try to avoid fractions when you talked about fractional parts of a circle. In other words, look at how many whole numbers 360 is divisible by. In fact, let me just write them down for you so that you can see for yourself. Can you read this okay? See, 360 is what? It's 2 times 180, 3 times 120, etc. Look at all the numbers that go into 360. 2, 3, 4, 5, 6, 8, 9, 10, 12, 15, 18, 20, 24, 30, 36, 40, 45, 60, 42, 90, 120, 180. See, in other words, if you're talking about 1/4 of a circle, it's what? 90 degrees. 1/3 of a circle would be 120 degrees. 1/12 of a circle would be 30 degrees. And by the way, if you'd like some folklore, okay, stop to think about this for a minute. What's the name of the 12th month? The questions get harder, don't be nervous. 12th month is called December, isn't it? What does DEC stand for? Not 12, but 10. What's the 9th month? The 9th month is September, isn't it? But SEPT, S-E-P-T, stands for 7. October stands for 8. You see, originally, we had 10 months, each with 36 days, because 360 would have been a nice number of days in the year, because that way, a lot of fractional parts of a year could have been a whole number of days. What happened was, there were 365 days in the year. By counting 360, the seasons got sort of messed up, because every year, you were losing 5 days, and pretty soon it would be snowing in June rather than in March or February. So that's when Julius Augustus Caesar augmented the calendar by adding the months of July and August. You see, with 365 days, by the way, just as an aside, 365 breaks down to 5 times 73, and 73 is a prime number. And that means that what? With 365 days in a year, the only fractional part of a year that come out to be whole numbers are 5ths and 73rds. And by the way, speaking of prime numbers and the like, you know, back when you were learning fractions and you wanted common denominators, you broke things down into prime factors. I thought I'd like to show you how you can guess what numbers go into Let me just show you how prime factors work over here. So you take the number 360, it's divisible by 2. 2 goes in 180 times. 180 divisible by 2 is 90. 90 divided by 2 is 45. 45 is divisible by 3, gives me 15. 3 is divisible by 15, gives me 5. So 360 breaks down to what? 2 times 2 times 2 times 3 times 3 times 5. Look what that means then. What it means is I can now look at these prime factors and figure out every number that goes into 360. See, suppose I take the prime factors one at a time. What are the different prime factors here? 2, 3, and 5. Now, what if I take them 2 at a time? I could take 2 2s, which would give me a 4. I could take a 2 and a 3, which would give me a 6. I could have taken 2 3s, which would give me a 10. I'm sorry, I could have taken 2 3s, which would give me a 9. I could have taken a 2 and a 5, which would give me a 10, and a 3 and a 5 that would give me a 15. And I could list them 3 at a time, etc. This goes on a lot in math, by the way. You know, there are 5,280 feet in a mile. It would have been easier to remember 5,000. But the reason we picked 5,280 is look at the prime factors of 5,280. You have 5 factors of 2, a 3, a 5, and an 11. So a lot of fractional parts of a mile will be a whole number of feet. On the other hand, with 5,000, that's 5 times 1,000. Each 10 is 5 times 2. And see, the only prime factors you would have were 2s and 5s. Here you also get what? 3s and 11s. But that was just meant as an aside. Let's now go back to angular measure. See, what I can now do, with a circle divided up into 360 degrees, they have an instrument called a protractor. It looks like a half moon. It has degrees measured on it from 0 to 180. And when you want to measure a particular angle, you put the protractor down on one of the sides and start over here, the point you want to measure from. And if you want to say a 42-degree angle, you'd measure over here, you look over here to 42, then draw this line. That would be a 42-degree angle. By the way, going back to the idea of 12 o'clock and 6 o'clock, see, what's going to happen is we'll start measuring in this direction. This would be a 0-degree angle. Okay? Now if you go 1/4 of the way around the circle, 1/4 of 360 is 90. So this would be a 90-degree angle. See? So this is, instead of saying 3 o'clock, this is 0. This is 90 degrees. This direction is 180 degrees. See, all the way around here. Half the circle is 180 degrees. Down this way is 270 degrees, right? And, okay, all the way around to here is, but by the way, you don't call it 0 degrees anymore. It's, you've gone all the way around the circle. It's 360 degrees, but a 360-degree angle goes all the way around the circle, but nevertheless, what does it do? It winds up in exactly the same place that the 0-degree angle wound up in. Now, if we want to take this as a compass type of thing, notice that if you want to split the difference between east and west, if this was 0 degrees and this was 90 degrees, this line here would be what? 45 degrees, etc. Okay? And what this does now is brings us back to the completion of our mission. After all, what was our mission before? Our mission was to discuss a way of looking at directed lengths, vectors in the plane, in terms of a magnitude, how far they were from the origin, and an angle, because our hunch was that somehow in multiplying two of our new numbers, we were going to have to do something with the magnitudes and something with the angles. And that's what we want to investigate right now. So let's just take a look and see what we do now. Okay? Up until now, what we said was what? That if you have a point in the plane, which we would have called x comma y, if we want to use vectors, this vector here is 1. This vector here we showed last time was I. So x comma y really is the complex number x plus iy. Now, another way of writing this complex number is let's measure the angle and the distance. In other words, here's O. We see how far away the point P is, and we're going to call that R. The distance is going to be R. Then we measure the angle that the line from O to P makes with the positive x-axis. And we're going to call that angle theta, because that's a Greek letter, and we're calling it theta. Well, we're not calling it theta. We're picking theta, not because we want to confuse you, but traditionally, this is the name given to the angle when we're using polar coordinates. So you see, I can name this point P by telling you how far in the horizontal direction and how far in the vertical direction it is from O. I can also name it by telling you what? How far away it is and what direction it makes. In other words, this is sort of a circular thing. It's called polar coordinates because you can look at the point O as being your so-called pole, where you're measuring from. See, if I tell a person I'm R units from O, that means what? I can be any place on the circle centered at O with radius equal to R. Now, where does the angle come in? See, if all I tell you is how far away the point is, that's what we were talking about before. If I tell you that the absolute value of OP is R, and this length here is R, so far P could be any place. But as soon as I give you a specific angle, that locates the point uniquely. See, there's a whole bunch of lines I can draw that have the same distance R, but as soon as I say that the angle with the positive x-axis has to be this, now you see I've located specifically just one point P. So let's take a look and see what this means. What this means is the number 1 in polar form can now be represented as 1, the polar distance is 1, and the angle is 0. See what I'm saying? Here's 1. So this is what? 1 unit. And the angle with the positive x-axis, there is no angle. They're in the same direction. It's like at 3:15. The two hands of the clock are together. That's a 0-degree angle. Now, what happens when you multiply by 1? When you multiply by 1, right, you don't want to change anything. See, in other words, based on what 1 has to mean, what should happen when I take the point r comma theta? And I multiply it by 1. I should still get back what? R comma theta. But let's see what happens over here. Another name for 1 in this system is what? It's 1 comma 0 degrees. Well, let's look at the problem. Let's look at the answer. There was an r here, or 1 here, and the answer had r. So our hunch would tell us that we multiplied the two r values. See, r times 1 would give you r. On the other hand, here was theta, here was 0, but the angle here wasn't 0, it was theta. How can you combine 0 and theta to get theta? To add something onto something without changing it, you see, must mean that what you had was adding 0. In other words, you must have added this thing. See, in other words, would this be correct? If I multiplied the r times the 1, I would get r. If I added the theta and the 0, I'd get back to theta. So based on that information, here's what I'm going to do to define multiplication. In polar form, if I multiply two directed lengths, and I'll illustrate this for you in a minute, but let's say that one of the numbers is 2 comma 30 degrees. And what does that mean? It means you go 2 units from your pole at an angle of 30 degrees, which you can measure with your protractor. My other complex number is going to be 3 comma 15 degrees. What does that mean? I'm going to be 3 units from my pole at an angle of 15 degrees. I will draw that for you in a minute. But what's my rule going to be? To multiply these two, I multiply the two r values. 2 times 3 is 6. And what do I do to the angles? I add them. 30 plus 15 is 45. And to show you that in terms of a picture, here's what I'm saying. Drawn to scale, this line here, this black line here, is 2 units long at an angle of 30 degrees. Okay? Now, what do I want to do with 3 comma 15? Since I'm going to add the angles, what I'm going to do is I'm going to take the second number, assume that it begins over here, right? Mark it off. See, in other words, I mark off that angle, put this together this way, and what am I going to do? I'm going to add the two angles. See, the 30 plus the 15 gives me 45. And what do I do to the lengths? I multiply the 2 times the 3 to get 6. In other words, what I first do is, starting with the 30 and the 15, I simply add the angles to get 45. Once I have this direction, what do? I multiply the 2 times the 3 to get 6. In other words, I can take the 3 units, mark it off twice, to give me the 6 units over here. Now what this does is it gives me a very interesting way to revisit multiplication. Let's, for example, look to see what happens when you multiply by -1. See, in this new number system, it's no longer called -1. Remember, we're dealing in 2 dimensions now, the whole plane. How would -1 be written in polar coordinates? -1 is over here, isn't it? So relative to this line, to this direction here, relative to the positive x-axis, to get this direction, what do? I have to take a 180-degree angle. I have to go halfway around the circle to stop moving in this direction. And how far do I go? This is 1 unit. So -1 means what? See, again, see if you follow what I'm saying. -1 means you draw a circle of radius 1 around your pole, and you now make a 180-degree angle. And there's -1. Okay? So -1 in polar form is 1 comma 180. So look what happens. When you multiply 2 times -1, in polar coordinates, that's what? 2 comma 0 degrees multiplied by 1 comma 180 degrees. We multiply the two r values. 2 times 1 is 2. We add the two angles. 0 and 180 is 180. What does 2 comma 180 look like? It's what? You go 180 degrees and 2 units in that direction. So 2 comma 180 is this point over here. Isn't that the point that was called -2 before? Now look what happens when you multiply -2 times -1. It's going to give a whole new interpretation to why negative times negative is positive. See, -2 we already know is what? 2 comma 180. -1 we already know is what? 1, 180. How do you multiply two of these numbers in polar form? You multiply the two R values, 2 times 1 is 2, and you add the two angles. 180 and 180 is 360. But when you go 360, doesn't that bring you back to the same starting place? See, be careful here. A 360-degree angle is not the same as a 0-degree angle. What is true is that what? They look the same. You see, if you go all the way around the circle, you may come back to the same place. But if you were driving, you've used up some gas, haven't you? It's not the same thing to stay there as just to go around the circle. It's just that if you went once around the block and nobody saw you, they would come back and see you standing in the same place and wouldn't know that you've moved. But see, this is quite true in general, and it's something that we should keep a little bit of a handle on just for the sake of completeness here. Suppose you had an 1100-degree angle. How would you draw that? Well, again, what I want you to see is the 1100 degrees. Every time you go 360 degrees, you're back to where you started from. So divide the 1100 by 360. 360 goes into 1100 3 times with a remainder of 20. That means 1100 degrees can be written as 3 times 360 plus 20 degrees. So what that means is, starting here, what do? You go around the circle once, twice, 3 times, and then what do? 20 more degrees. In other words, an 1100-degree angle is certainly more motion than a 20-degree angle, but what happens is what? When you measure the 1100-degree angle, it ends in the same position that the 20-degree angle would have ended in. By the way, in advanced math, in complex number theory, this concept is very important. And how many times around the circle you go is actually given a special name called the winding number. And every time you go around that circle, something important happens. So you must never confuse an 1100-degree angle with a 20-degree angle. And by the way, this doesn't just work for angles. It also works for anything where things go around in a cycle. For example, every 7th day brings you back to the same day of the week, doesn't it? So for example, suppose I say to you, if today is Tuesday, what day of the week will it be 212 days from now? Well, one way is awful to do. You can say what? Wednesday, Thursday, Friday, Saturday, Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, and keep counting till you've counted off 212 days. The smarter way of doing this is to divide the 212 by 7 and see what happens. Well, 212 divided by 7 is 30 with a remainder of 2. What does that tell us? Look, this tells us that 212 is what? 7 times 30 plus 2. Well, the point is, if you count off 7 days 30 times, every 7th day brings you back to the same day of the week. Okay? So therefore, 7 times 30, if you start on a Tuesday, the 210th day is still going to be a Tuesday. The remainder over here tells you what? How many more days to count off. In other words, 212 days from Tuesday, it's going to be Thursday. But it doesn't mean that only 2 days went by. 212 days went by, but it's only what? 2 days further into the week, as days are named, rather than it was before. And this idea stays quite important in mathematics. There are many, many times where, surprisingly enough, the remainder is more important than the quotient. And we're not going to talk about that, but I just wanted you to see how many topics from basic arithmetic keep coming up as we get advanced even. And what I am hoping, and let me just confide something to you, very few algebra books introduce the extended number system this early into the course. My feeling is that the earlier an advanced and potentially scary subject is introduced, the less harm it's going to do. In other words, the earlier you learn something, the more it settles before you have to use it again. And the idea of complex numbers is so important in advanced mathematics that I want those of you who intend to pursue a mathematically oriented career to know about this. For those of you who aren't, to me, the beauty of this is that the idea of drawing lengths and measuring angles is something you can do in the 2nd or 3rd grade. It'll help you develop your small motor skills. Measuring an angle, draw a length. How difficult is that? How scary is it to say, draw a line in this direction that's 5 units long? And to invent an arithmetic using lengths and angles might appeal more to visually oriented people than doing it the way we do. But this is no time to philosophize as we start to run out of tape. Let me just close here, say we'll continue this topic in our next lecture when we're going to show you the amazing property that the number I has, and just so you don't stay in suspense, that's going to be the number whose square is -1. I is going to be a number that satisfies the equation x squared plus 1 equals 0. But rather than spoil the whole party now, let me close by having you once again do what? Study hard, have fun, stay young. I'll see you next time.